Folks, boy, it's really sparse today. So there will be a quiz at the end of the lecture. The DigiKey order is in. First DigiKey order is in. And we will go to a modified schedule on Monday morning. So as of Monday morning, you should check the schedule section of the web page to find out when we're going to be open, but it'll be most evenings and quite a few hours on the weekend. We still, of course, cannot overlap 2300. Oh yeah, I've been playing around a little bit with the idea of trying to make an infrared data link for these CPUs rather than a radio link. Anybody have any thoughts on that?
Would that be very slow?
Well, it can be up 100 kilobits or so. It can be as fast as a RS-232 link.
I remember when cell phones used to have only IR communication, and like you had to have the phones like this, and it was very, very slow, and then we got Bluetooth and so slow.
Right, and there's a direct link between the amount of energy you put into the link and the speed of the link, but it's not unreasonable to get a 50 kilobits at a meter now. So thought I'd talk a little bit more about motors today, and mostly want to talk about stepper motors because they're very nice. They're digital motors. But before I talk about those, I'd like to just more generally talk about actuators and the kind of ways you can move things. And feel free to add in any that I don't mention. But the one we've talked about, we've used so far, is so-called DC motor, which is you put a voltage on it, it spins. But there are other systems that are quite useful. One is a servo motor. And that's a DC motor that has internal feedback in it so that it is more controllable. Servo motors have 3 leads. You would have a +5, a ground, and a control lead. Control lead is a pulse width modulated system with a minimum time between pulses of 20 milliseconds and a control such that when you're at 0 degrees corresponds to about 0.5 millisecond pulse width, and 270 degrees corresponds to about 2.5 milliseconds. So it's a natural to control from a microcontroller because it's quite easy to generate a pulse width of a fixed length. And so if you need to, say, scan a sonar head through 180 degrees or something of that sort, then having a servo motor is a natural thing to do. Using a servo motor is a natural thing to do rather than trying to control a DC motor to be position feedback. So in this case, the pulse length determines the shaft position. Servo motors are variously, yes?
I have a question. So is the difference between a servo motor and a DC motor just the electronics that are attached to it?
Yeah, it turns out that inside servo motors are a small DC motor and a gear train and a feedback system. But from the outside, they become positionable by a pulse width. Now there's a modification which is often done to a servo motor which turns the pulse width into a speed control. And you see these in robots a lot. The pulse width now becomes the speed at which the motor rotates. So it's no longer a position control, it is now a speed control. And pulse widths of less than a millisecond or so cause the motor to go backwards, and pulse widths greater than a millisecond or so cause the motor to go forward. So you have direction control as well as speed. What other kind of actuators can you think of? Linear actuators, like for instance a loudspeaker. A loudspeaker is a high bandwidth linear actuator, relatively small travel. You typically only get a few millimeters unless you have some gigantic bass driver pushing a couple of centimeters. But the nice thing about speakers is that they are high bandwidth. Typically there's a coil that's moving some sort of diaphragm back and forth. They're high bandwidth, and so you could, for instance, put a small mirror on one and move a laser beam back and forth very quickly by changing the angle of reflectance at audio rates. So if you need very high bandwidth but not too much motion, speakers are quite useful. There's a version of servo motor which is a linear motor, and there are also versions of stepper motors I'll talk about which are linear motors. What else? Anybody have any experience with piezo motors? Piezoelectric motors? So piezoelectricity is a phenomena where a piece of material changes size with electric field. And if you have a large enough change in size, then you can treat this as a linear actuator or a rotary actuator and move something around, typically a few microns, but sometimes as much as a millimeter, but with phenomenal force. So if you need to move, say, an atomic force microscope around, you use a piezo actuator because you can get submicron accuracy at very high bandwidth and very high force. Another possibility is a solenoid. Anybody ever actually used a solenoid in this class? A couple of people have. Oh, or a few. Right. It's a coil. It's an electromagnet with a piece of iron hanging in it. You turn on the magnet, it pulls the iron in. It is all or nothing. This is not a proportional device. It is digital. It is either out or in the coil. The armature is either out of the coil or in the coil. Nothing in between. It would be good for digital-like motions. For instance, pulling a bolt out of a door lock, where you want it to be either completely out or completely locked, but you don't care much about what happens in between. Or, as in the case last year of automatically opening a birdhouse so that the door will flop open and the bird can get out without having to have a human there scaring the heck out of the bird when you open the door. You can, to a small extent, you can control how fast it is by the current you put through the solenoid. But basically, you get up to some threshold, and the armature snaps into the coil. Partly because once it starts to move into the coil, the field gets greater, it moves faster, so you get a feedback situation that drives it into the coil. Some are. If you have two coils, you can control them two directions, but usually there's some sort of spring out here that returns it out, pulls it out. There's a very interesting actuator I've seen used a few times in this lab. It's very slow, typically a second. It's called it's a memory alloy called nitinol wire. Nitinol, nickel titanium, I think. And it has the interesting property that when you put enough current through it to heat it to 50 degrees C or so, it shrinks by 2 to 5%. All right, so you get this wire that shrinks, and a wire that's 0.05 inches in diameter produces a few kilograms of force. You say, oh, well, 2 to 5%, who cares, right? So there's something this long is going to move a weight maybe half a centimeter off the table. And that doesn't seem like much, but after all, your bicep only changes length about 2 or 5% when you contract. And the reason you get so much motion in your arm is that you have a long lever out here to amplify the amount of motion that the bicep produces. And so, because the force is so great on a nitinol wire, you can make a thing that looks an awful lot like a limb with the wire attached up here. You put some current through this wire, it shortens 5%, and this moves up, just like your forearm. The advantage of it is it's completely quiet. It produces no sound at all. And it's reversible. So you have to have some weight on here so that when you turn the current off, the arm comes back down again. It's reversible over several thousand actuations at least. And the forces are quite large. It's used in robotics quite a lot, particularly if you want to make something that kind of moves like a very slow animal. So there's one guy named Ayer, A-Y-E-R, who built a robotic lobster funded by, guess who? DARPA. What would you use a robotic lobster for? Underwater spy. Cutting cables. Did I hear the word ridiculous? I have to agree. But hey, if it funds biological research, it's okay with me. So there's lots of ways of doing actuation, and if you've got some weird geometry or something you need to put in a small place or have fast motion, we can talk about it. But what I mostly want to talk about today are stepper motors, partly because a couple of people have already asked me about stepper motors. And I'll talk about two kinds, so-called unipolar and bipolar stepper motors, which are different in the way you drive the current through them. Stepper motors are inherently digital. If you take the shaft of a permanent magnet stepper motor, and that's what I'm going to be talking about, are permanent magnet stepper motors, and you turn it, you can feel it go click, 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 click. And even a very cheap motor has perhaps 40 detent positions per revolution. And it will produce torque. It'll produce a holding torque at zero current, because it is a permanent magnet being attracted to soft iron. So the geometry, this very simplified geometry, oh, I could do a little better than that, I guess. The geometry is that there's going to be some permanent magnet north-south, some bar magnet inside this thing, and then there's going to be a multiple set of magnetic poles that are nearby the magnet. And in the case of a bipolar motor, there is a coil around that's actuated either with current going this way through it or this way through it to change the polarity of this electromagnet. And then there's another set of pole pieces connected to another coil that is at right angles, and in fact most motors have several sets of poles to get a finer angle than 90 degrees. But the motion here is, the scheme for controlling this is that at zero current, a south pole is induced up here that produces some torque to hold the motor in position. Not much torque, but a little bit. And when you freely spin a motor, excuse me, when you freely spin a motor, that's what you feel as sort of a clicking a detent as you rotate the motor. To produce more torque, you put current through this coil in such a direction that this is a south pole and this is a north pole produced by the current flow. And that'll hold the motor actively at that position. Now let's say, while this current is still on, you put current through this coil in such a direction that this is a south pole. What's going to happen to the rotor? It's now going to rotate to a position at maybe 45 degrees between those and stay there. Now if you turn off this pole and leave this one on, the motor is going to turn to this position. And you've just done 1/4 of a revolution. Now you make this a south pole by changing the direction of the current in this coil, flipping the direction of the current in this coil. You make this a south pole here. The motor moves to this position. You turn off this coil, and now the motor moves to this position. And now you've done a half turn. So the challenge here then is to produce a pulse sequence on two coils, an overlap pulse sequence on two coils, to move the motor in the direction you want by causing the south pole to either move clockwise around these pole pieces or counterclockwise around the pole pieces. Any questions? And there's all kinds of drive schemes. But first of all, let's talk about driving the current here. You want to be able to drive a current either through the coil this way or through the coil this way. You typically want to use only one voltage source, not a split voltage source. And this implies that you have to have a switching setup that will route current in one of two directions through two leads. And what is typically used is a switching setup that looks like this. So you have V plus up here, you have ground down here, you have the motor winding between four switches. 1, 2, 3, 4. Usually those are not physical switches, usually they're transistors of some sort, but never mind. And so if you were to close switch 1 and 4, then you would have current flowing this direction. If you close switches 2 and 3, you have current flowing this position, this direction, and so you can do a full reversal of the current with this device. Because of its shape, it's called an H-bridge. If you close switches 1 and 3, you destroy something. All right. I have seen many a whiteboard melt. All right. So, let's say that you were controlling these switches directly off of 4 lines of the CPU. And so software is generating the 4 control signals. any mess up in the code. Let's say that the chip was programmed weirdly when you turned it on because of the last project that was on it. Your H-bridge is history. All right, before you even program the chip. So, the rule is you never, never use software to decode an H-bridge drive. You do it in hardware. Or, a much more reasonable thing to do is you buy the H-bridge. They cost pennies to dollars depending on the current level, but you can buy a 1 amp or 2 amp H-bridge for around $1. Why would you possibly build it? Because you ran out of time. But think ahead. Don't build H-bridges. But even then, with the H-bridge, we have to figure out what kind of a pulse sequence we want. And there's at least a couple of different kinds. One is called the wave pulse sequence. So let's say we have phase 1 and phase 2, where now we're talking about the current through phase 1 and phase 2. We could have something that looks like this, where we put some current through phase 1, and then we bring it back to 0, and then a little while later we put some current through phase 2 to bring the armature around. In this case, we're going to have the magnet held here, the permanent magnet armature held here. We're going to turn this coil off, we're going to turn this coil on. This is going to go snap to this position. This is a low torque alternative. And the reason it's low torque is that when you turn this magnet off and turn this magnet on, the pole piece is quite far from here, and so the attraction is not great. So the torque generated is quite time variable. The alternative is you turn this coil on, as I said before you turn this coil off, which is called a full step. And for a full step, phi 1 and phi 2 are going to look more like this. But I'll start this. So we're going to have 0 here, and we're going to step it positive and negative continuously, and phase 2 is going to be 90 degrees out of phase, looking like this. Whereas with a wave, we're going to turn on phase 1, turn it off, turn on phase 2, turn it off, turn on phase 1, turn it off, turn on phase 2, turn it off. The advantage of the wave is that even though the torque is less, the current is less. So the average power is lower. So let's say you overspec your motor and you don't need all the torque it can produce, then you might go to some scheme like this. Whereas if you underspecified the motor and you need all the torque it can produce, you might go to a full step option. Also, there's another condition. Let's say you're starting your motor from 0 RPM and you want to get up to some fairly high speed. The torque is proportional to angular acceleration. Remember that from someplace? And so the more angular acceleration you want, the more torque you have to have, which means the denser the waveform has to be. This brings us to a very basic limit. As long as you stay below a certain torque level, as long as you stay below the torque that the motor can generate, the motor is digital accurate. It will go exactly 1 step per pulse. No more, no less. If you have the motor try and produce more torque than it can produce, then it'll start to slip phases, and it'll no longer be digital accurate. We've had people do open loop control in the past where you set up the system. This was an interesting use of a. They took two stepper motors, put them up here on a blackboard, on a whiteboard actually, and ran fish line down to a magic marker, and then they positioned the magic marker over the X, and then after that the motors ran open loop. They didn't measure the position anymore. They just knew that they were producing enough torque not to slip, and they could move that pen around and draw on the board. The coordinate system is very odd. The natural coordinate system is a circle around that point and a circle around that point, and to do anything useful you have to orthogonalize that coordinate system. So it turns out you have to solve a Jacobian, but not so bad. You can run them open loop, you can run them digital accurate, as long as you don't exceed the torque limits, which means that as you accelerate, you have to slowly increase the pulse frequency, and you have to slowly decrease the pulse frequency. If you just go from 0 to full pulse rate, it's going to slip for a while, and you won't know where the motor is anymore, unless you have some sort of extra feedback. So then the microcontroller is going to generate this pulse sequence, probably through some kind of direct digital synthesis. But instead of having a sine wave in the table, you're going to have some sort of pulse train in the table. It's either going to be the table entries are either going to be something that looks like this for one cycle, or something that looks like a square wave for one cycle. You set the phase of phase 2 either 90 degrees leading or 90 degrees lagging, and you will have motion either clockwise or counterclockwise. Any questions about that? So these motors are sometimes called 4-wire motors because there's 4 wires coming out of them. And sounds obvious, but so the alternative then, you get 4-wire motors around a lot. You get 6-wire motors and 8-wire motors. 6-wire motors are unipolar motors, and they have a coil structure that looks like this, where you have a center tapped coil on each phase, and you either drive current, typically you wire this to the plus, and then you either ground this side or you ground this side. Likewise here, you either ground this side or you ground this side. An 8-wire motor just splits each of these coils in half and brings out all of the possible wires. And an 8-wire motor you can either wire for unipolar or bipolar. But most motors are either 4-wire or 6-wire. If it's 6-wire, you say, well, why would you do this? Well, it turns out the reason for doing it is that it's easier to drive. Because instead of taking 4 transistors per phase, per coil, it only takes 2 transistors per coil. So you have the complexity of the external circuitry. That's good. What's bad about this? There's a little difference in the algorithm. It's not so much worse, but it is a little different, yeah. Size, yes. Because, exactly, you have to double the coil size for a given torque. Quite right. Or put it differently, at any given time you're only using half of the coil. And so you only get half the torque for the same coil mass. Nonetheless, you see quite a few unipolar motors around, because if you don't need very much torque and the drive circuitry is cost sensitive, then you go this way. I have some, I think I've down to my last two $1 unipolar motors. They've been used for everything for 10 years or so. I bought 100 of them for $1 each. And they sure did run hot. You run them at 12 volts, full overlap phase, and they get too hot to touch by a lot. So too hot to touch normally means about 120 F, 130 F. And these I'd say were below boiling, but above 150 F. So they emboss your fingertips nicely, but they didn't care. You don't want to put them in foam core though, because it'll melt. Also, it sort of does a job on hot glue if you're building robots with hot glue guns. So the structure of the pulsar here then is going to be to, if you call this let's see, A, B, C, D, switch A, B, C, D, that you're going to have the wave version of this is going to be to put out a series of pulses that look like this. So you'll close the switch here, and then you'll close the switch here, then you'll close the switch here, then you'll close the switch here. And you'll produce a series of pulses that, for one direction of rotation, B comes after A, and for the other direction, B comes before A. Change the phase of those. And if you want to do a full step version for a unipolar motor, so full step unipolar, then you're going to have something that looks more like this. A, B comes up at 50%, C comes up at 50%, D. So that you always have overlap of the torque on each coil. Any questions? So how do you drive these things? Well, again, I would not build an H-bridge. There's a couple of reasons. One is you actually need more than 4 transistors because you have to do level translation. And you may have to do isolation depending on how bad the noise is. You can buy packages which are isolated level shifted H bridges, but you can certainly buy them that are just level shifted and ready to go. I think an LM18200 is an H bridge that's appropriate. The only problem with the 18200 is that the pinout, it's in sort of a package that looks like a gigantic TO120, TO220, but the pinout looks like this, with 1 centimeter, with a 1/10 inch spacing between each one of these, which means there's no way you can fit it into a whiteboard or any other board that we have. So that's kind of tedious. You may find that, well, probably no matter what kind of H-bridge you get, if you're going to put significant current through it, you're going to have to heat sink it somehow. So you want to find a package which is both solderable and heat sinkable.
In case anyone's curious, Pololu or Pololu, I can pronounce it, that website, they make a dip-socketed stepper driver that has like the stepper driver on it and VREF circuitry for setting the current, the stepper motor and all this stuff, and all you have to do is send it like step, direction, and enable from the microcontroller and the rest of it.
That's a good point. And my next few sentences are going to be that you don't have to do the pulse generation yourself even. You can buy integrated circuits that will take a command like run forward, run back, and plus a few lines for speed, and the high-level controller will take care of all of the pulse sequencing for you. So you don't have to roll it yourself. If you want to, we have some switches in the lab, ULN, what is it? ULN 2803s, which have 8 copies of this circuit in them. There's a current limiting resistor around 1K, a NPN transistor, a protection diode, so you don't have to worry about that. In fact, it has 2 protection diodes, so that you go to the coil here. This is the motor coil. And internally is another protection diode, which then goes to V+. So there's 8 channels of this inside one integrated circuit. And they're each rated at about 500 mils with no heat sinking. Again, it runs pretty hot, but who cares? Because there's stepper motors everywhere. There's stepper motors in printers, there's stepper motors in scanners, there's stepper motors. Well, I don't think there's a stepper motor in my cell phone. I don't think. But there's stepper motors almost every place. There's a vast number of drive circuits available. You can get them everywhere. Pololu, let's see, I have to look at the name of this one. I can't remember it. Ferretronics. Paladin Semi. Ferretronics. I think they were bought by Paladin. Paladin Semi. That might not be spelled right. Wait a minute. P-A-L-A-D-I-N. P-A-L-A-D-I-N. You know, these vowels are all kind of interchangeable. Except when you're searching on the web. And you can do things like give it commands to ramp up in speed, using some of the stuff from Paladin Semi. Ramp up in speed, ramp down in speed, single step, set the step rate, set the number of counts. So go forward 35 counts and stop. So there's lots of high-level solutions to this. Probably what most of you will do is to roll your own, in fact. will be to use a low-level driver like a ULN 2803 and to get the power necessary to run the motor, and then drive these directly off of port pins. If you're using unipolar motors, you can get away with this because there is no set of switches that will destroy a transistor. If you're using unipolar motors, you have to use a decoded H-bridge. If you decide to build your own H-bridge with the level shifters and everything, then you will have to build the logic circuits, hardware TTL logic, necessary to decode them, so you cannot possibly turn on the wrong set of transistors at the correct time. And I have some stuff online on how to design that. It's, I think, two TTL packages. Who's going to use a stepper motor? For what? I can't remember.
Moving an assembly back and forth across the piece.
For robot drive wheels. Solar tracker. Right. Any other motors? Servos? No motors? So that's run them as fast as you. No, they have to be controlled also, right? For attitude control. So you'll have to do some speed control, but you'll be using that through closed loop feedback of the attitude, right? Okay, folks, take out a piece of paper. Full size, 8.5 by 11, please. No little tiny pieces of paper.